Hello and welcome once again. This is Mr. Buchanan, and today we're going to be talking about simplifying radicals. So, first we got to figure out what exactly is a radical. Well, the word radical, comes from the same root word as radish, which means root. Okay, so a radical is a root. So what exactly is a root? Well, a radical and a root is the opposite of an exponent, just like adding is the opposite of subtracting. So when you take a root, so let's say we take a root with an index of 2, or a square root, of something that's squared. That square root and that squared part will cancel out and give me whatever I have underneath the radical. So, speaking of which, we need to go over the terminology so we can talk about this a little bit more freely. So, here we have a root, or a radical, and the n here is called the index, and the thing underneath the radical is called the radicand. Alright, so when we talk about simplifying radicals, what we're actually meaning is that we're going to take all of the square roots inside the radicand and we're going to factor them out. Now the main reason why we're doing this is so that we can add two radicals together. So I mean, if we have two things with the same radicand, we can add them together. If the radicands are different, or if the indexes are different, we can't add them together. This also supposedly makes it easier to estimate, although sometimes that's harder than you would think. There's two methods for doing this. The first one is to figure out what perfect squares are inside the radicand and then factor them out using a multiplication property of radicals. Now this method really only works with square roots. Okay, otherwise you have to think about perfect cubes or perfect numbers that have a degree of 4 or 5 depending on what your index is. So this method does have its flaws, but it is very quick if conditions are right. So let's do an example of this. So here we have the square root of 32. Now, going through your perfect squares, some examples of perfect squares are 1 squared is 1, 2 squared is 4. Now I could use 4 in my factorization here, or my simplification here, and it would work. But I would have to do it more than once. I want the biggest perfect square that goes into my radicand. So let's keep going. 3 squared is 9. Nope. 4 squared is 16. Now 16 goes into 32. To make sure there's nothing bigger though, you can keep going until you get 2 or above 32. So 5 squared is 25, and then 6 squared is 36. 36 is bigger than 32, so I know the biggest thing is 16. So 32 is equal to the square root of 2 times 16. Now, my multiplication property that I was referring to earlier says that whenever you have two things being multiplied together in a radicand, you can split them up like this. So the square root of 2 times 16 is the same thing as the square root of 2 times the square root of 16, which is the square root of 16 is 4, so it's the same thing as 4 times the square root of 2. And when you multiply like this, you actually don't have to put that little dot in between. It means the same thing as if you just write it like that. That means 4 times the square root of 2. You might also pronounce that 4 square roots of 2. That's also acceptable. So, let me talk about the other method that I use, which is called jailbreak. And I'll explain the jailbreak name in a minute. We've got a little anecdote about it. So, you start by making a factor tree of the radicand. You want to get down to the prime factorization of it. Then you find and circle pairs of the same number. And then for each pair you circled, you write 1 on the outside of the radical and cross the other one out. Then you multiply the outsides and multiply the insides. These two steps could be done at the same time. So now I'm going to redo this problem, and this time I'm going to do it using the jailbreak method. So when I make my factor tree, I always start and factor out all the 2's first. After the 2's, I go to 3. After the 3's, I go to 5. I don't do 4's because I've already factored out all the 2's, and so I've already factored out all the 4's. So I only go through prime numbers starting with 2. So 32 is 2 times 16. 16 is 2 times 8. And then 8 is 2 times 4. And 4 is 2 times 2. So now I have all prime numbers. I can circle my pairs. Now that I've circled my pairs, let me go through the anecdote. So, in this story, the radical here is like a prison. Your index is the prison security level. If the index is 2, that means 2 prisoners have to try to get out at the same time in order for one of them to make it out, which means the other one doesn't make it out. If your index was 3, then that'd have to be in groups of 3 for one of them to make it out. The other 2 wouldn't make it out. So this actually works for any index. You just change the number that you circle whenever you're circling your groups of numbers. The numbers on the inside right here, this 32 represents all the prisoners being multiplied together, the prisoners being the numbers. So when we factor it out, we see all the individual prisoners. So whenever we're simplifying, we've circled our pairs. These 2 try to make it out. Bang, that one gets shot. The other one makes it out. In this group, same deal. One gets taken out. The other one makes it to the outside. Now, if they didn't have a partner to go with, they stay on the inside, like this 2 right here. Now, if there was more than one thing on the inside, we'd multiply it together, but there's not, so we leave it alone. We do multiply the stuff on the outside, so we get 4 square roots of 2 as our answer, and that was the exact same answer we got doing it the other way as well. Alright, so let's reiterate when to use each method. So method 1 is quick and painless as long as you know what perfect square goes into the radicand. The flaws of that one, though, once again, is it doesn't really work that well for larger indexes. Okay, and larger numbers in the radicand. Method 2 always works, so use it whenever you want to. The only downside of that is sometimes very big numbers have very large factor trees. So you may be making a very large factor tree to figure out your answer. But it always works, always gives you the right answer. Alright, this has been Simplifying Radicals. I hope I have helped. You can always search for other things. Just search for Simplifying Radicals online, and you'll find plenty of resources if you need more help. I think Khan Academy does have Simplifying Radicals, so you can always check out there for more practice. And have a good one.